All right, so here we are. Let's do dot products. All right, so dot products. So the dot products here, if we give two vector, the dot product is denoted by, to do the dot product, so you denote it this way. So it'd be um, u dot b is how we say it, u dot b. And you just multiply the components. Okay, there should be no plus here. You multiply the components and add them together. Usually I don't have this many typos in my notes. Well, I will just have to be extra careful. So here we just do the dot product and add them together. And so the dot product is really quite straightforward. For higher dimensions, follow the same format. You just do it more, I'll show you. So here, if I wanted to find u dot b, to do this, I'm going to take 2 times -1. So it'll be 2 times -1 plus 4 times 4, 4 times 4. So it would be the first component multiplied together by the second component multiplied together. And so what we get here is -2 plus 16, which gives us, of course, 14. Here, the dot product of, let's do b. So it'll be u dot b equals minus, oops, that's no longer a vector. Notice this, if we do the dot product, another name for this is scalar product. And notice here we just get back a normal number again, right? The dot product feeds us back a normal number. The other way to do this is cross product, which we won't teach you here, but you'll see it later, and that gives you back a vector. So here I'll have -2 times 2 plus -2 times 5. So that gives me -4 minus 10. So this will be -14. Here, if we have higher dimensions, so u dot b in this case, so here we're in a higher dimension, it's going to be 1 times 3, so 1 times 3, plus 0 times 4, 0 times 4, plus 4 times -7, 4 times -7. So you just keep adding up the multiples of the dimension. So a's multiplied together, the b's multiplied together. In this case, the c's multiplied together, and you just add those all up. And so in this case, I'm going to get 3, I'm going to get plus 0, and I'm going to get 3 plus 0, and then minus 4 times 28, which this will give me minus 25. Don't you write notes with code? Yes, I write all the notes in code. So I'm staring at code, so it's really hard to see my errors while I'm typing because it all looks like code to me. You should show us how to do that sometimes. I could give you a brief snippet of how it's done at the end of this. Let me finish the notes and then well, here. Let's make my life super easy. Ta-da. So let's pretend I saw this error. I'll show you real quickly. Ta-da. And here's the notes. Note me. Oops. All right, so here I look at the notes and I'm going down here. I have to write in. Here's headers, footers, and all this. And so what it looks like, this is what they call LaTeX. And so here I have to put in Beck, L angle AB, L angle B, L angle A2, B2, L angle is a vector, is a dot product denoted here. Here I just accidentally put a plus sign, and so I just get rid of that. And then here's a line which does this. The frame makes the little frame around the box. BF series makes it the boldface font. And it's just a long, and then I just compile it, and then here it fixes it. Let's see. Okay. And so that's what the coding looks like, and that's how you do it. Wait, with the code? That's cool. Yeah. So that's how I have to write all these notes. And so I'm always looking at the code. I'm never looking at the compilation. It's called LaTeX. It takes about a term to learn if you just force yourself to do it. It's a good thing to learn. All math journals and all science papers are written in it. All science papers are written in it. So it's a good thing to know because I can't just type this into Word. It doesn't really work that well. I mean, I've seen people do it, but it's easier to just learn the coding and do the coding. All right, so let's do another dot product. So here I have u dot b. All right, so here I'll have 1, so 1 times 1. So the first components get multiplied together. Here I'll have -1 times -4, so plus -1 times -4 plus 2, 2 times -2. So this is 1. Negative negative would be plus 4. 2 times -2 would be -4. So this ends up being 1. Okay. All right, so some properties of dot products. Here we have u dot b is the same as b dot u. So it doesn't matter what order I do it in. Here, if I dot product, if I add up two vectors and then do the dot product, it's the same thing as dotting, doing the dot product of the two vectors and then adding it. Okay. If I have some scalar multiple here, I can put in the scalar in with u and then do the dot product. I can do the dot product and do the scalar, or I can put it in with b. The magnitude of the magnitude squared is equal to the dot product of a vector times a vector. Okay, so these are just some properties. It just tells you what you can and cannot do. All right, so let's look at, so we found the angle for a single vector, but let's pretend I have two vectors. So say I have a vector going like this and another vector going like this. And say we use the same initial point and two different terminals. Of course, the terminal points will be different. And I want to know what the angle is between them, right? And so to find the angle, so the angle between two non-zero vectors, the zero vector you have to throw away. So the dot product is also equal to the magnitude of v times the magnitude, or the magnitude of u times the magnitude of v times the cosine of the angle between them. Usually use this to say the cosine of the angle between them is the dot product divided by the magnitude. So, and notice two vectors are perpendicular if and only if their dot product is 0. Okay, so here, so this is the one we use more often because we usually want to know what the angle is between them. We can, if we know the vectors, we can easily calculate the magnitudes. And not often do we know the angle between two vectors and its magnitudes, but actually not know what the vector is itself. And in fact, it's not entirely possible to go backwards, because let's pretend I have a vector of magnitude 1, a vector of magnitude 2, right? And I know this to be a right angle, but can I reverse engineer what u and b were? The answer is not quite, because I could have this to be 1, this to be this, and this to be right angle. So here, I can spin it around, and it still equals the same. So you can't really reverse engineer back to what this was. All right, so let me show you how to calculate this. So let's actually do that. All right, let's do this. All right. Go ahead and do this, and then we'll talk about projections, and we'll do projections. All right, so find the angle between the following vectors. So here I have 3 and 4, and then -1 and -1 and 4. So let's just do this. So to find the angle, it's going to be the cosine theta is equal to u dot b. So u dot b in this case would be 3 times -1 plus 4 times 4 all over the magnitude of u and the magnitude of v. So the magnitude of u is the square root of 3 plus, or square root of 3, the square root of 3 squared plus 4 squared. And this will be the square root of 1 squared plus 4 squared. And so this is equal to the square root of 25 So this is just 5. This is equal to the square root of 17. Doesn't really simplify from there. So here I'll put in 5 square root 17. So this one and then this one. Simplifying that out, we get the dot product here becomes negative 3 plus 16. So 13 over 5 square root 17. And we'll just take, and then in order to finish this, hi, I need this. Hi, we don't need you everywhere. Hi, come on, hold on. Whoop, there we go. Type in the Wolfram Alpha. All right, so let's type in the arc cosine of 13 divided by the quantity of 5 sqrt 17. Nope, I typed in arc nothing. Arc cosine. Da, 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 da. So we have this to be roughly 0.8 or 50.9 or 50.9 degrees. So let's just type in 0.89. Okay, so that's the angle between them. Let's do one more example. This one should come out to be something very particular. I did it correctly, right? So here we have the cosine of theta is equal to, oh, let's figure out. So the magnitude here is -2 squared plus -2 squared. So that's the square root of 8. Here, the magnitude here, oops, is 2 squared plus -2 squared, which is equal to the square root of 8. Or 2 square root 2, but that's fine. Let's just leave it a square root of 8. And the reason is we're going to multiply them together anyways, and so it makes life easier. So here I'll have -2 times 2 plus negative 2 times -2 all over the square root of 8 over the square root of 8, or 8, right? So cosine theta, well, -2 times 2 is 4, plus -4 plus -2 times -2 is +4. So that becomes 0 over 8. Well, cosine of 0, well, that's, of course, pi over 2, right? We don't need to, oops, implies that theta is equal to pi over 2. Doesn't equal. This implies. And so here, we got a 0, so that means these are perpendicular. Does that pan out if we actually did it? Yeah, this would be -2 and 2. This would be 2 and -2, so like this, and so this does look like that. All right, so let's talk about the very last thing. So the very last thing is calculating projections. All right, so let's pretend I want to project one vector onto another. So what does this look like? Let me draw a little picture for you. So here I have some b, here I have some u, and I want to know how much of u, if I projected this down, what is u? U in the way of b. And I'll show you why we care about this in a second. I don't know if we'll do all the example problems I've shown you here, just because we only have 10 minutes, but and so this is the projection. So this is projection of u onto projection of u onto v. And then over here, this is, so we call this the projective component, and this is the orthogonal component, is what we call it, right? The orthogonal component. And so we simplify this and just call this u1, and we call this u2. And if I add up u1 plus u2, I'm going to get u, right? And so we call that to resolve or to break apart. So I can rewrite u as its parallel component, the part that's in the direction of v, and then the orthogonal component was the part that's against v. Okay. So let's do that with an example, and then we'll go ahead and And then we'll go ahead, we'll do at least two. We may not do the other two, I might just write skip on those, just because we're low on time. All right, anyway, so here we are. So here we have -2 in this. So here, in order to find this projection, so we want to resolve it into u1 and u2. u1 is just the projection. u2 is I'm going to take u minus the projection, right? So if I took this minus this vector, what's left is this vector, right? Because here, u1 plus u2 equals u, and so u2, oops, that's just normal u, there we go. So u2 equals u minus u1, which in u1's case is just a projection, okay? All right, so let's do this. I'll show you how to do this. You're going to do this on the homework. You're going to do this again on the exam. So we'll at least do two. And if I do one or two tomorrow, I'm not going to be sad about it. Okay. All right. So in order to do this, the first thing we want to do is find the dot product. So let's just find the components this time. Let's just find u dot b. Let's find b, the magnitude of b squared, and then we can put it all together. So u dot b in this case is -2 times -2 times -1, so it's 2 plus 9 times 2, which is 18, so this is 20. The magnitude of b squared is the square root squared, right, of, where are my components, where are b? So it'd be 1 squared plus 2 squared, so this would be the square root of 5 squared, so this just equals 5. Does that make sense? So now I can put it together. So I'll have 20/5. So u1 is equal to 20, or 20 times over 5, so 20 over 5, so 25ths times v. Well, what's 25ths? Well, 25ths is 4 times v, which is equal to, hold on, my brain just died. 4 times v would be 4 times -1, so it'd be -4. 4 times 2 would be 8, right? And then here to find u2, we're going to just take u, so we're going to have -2 +9 minus my projection, which is -4, 8. And so what do we have here? So when we take -4 minus minus of 4 will give me a +2. And then 9 minus 8 will give me 1. And so this is u2. So I resolve this into u1 here and u2 here. Now if I add these two vectors up, I get my vector u, right? This, notice here, the direction here is 1, 2. And so this vector here is in that exact same direction. So let me just kind of, I think it's worth drawing at least one of them. So let me just draw one real quick. So here I have the vector -1, 2. So it looks roughly like this. So this is my v. My u is going to be -2, 9. So like way up here. And then it needs to go out a little bit more. Hold on, I'm going to draw a little bit more to scale. Almost. Like this. And so here, the projection, well, I'm going to have to extend out my u. I'm extending out my v, and I draw it here. I guess I'm running into the other part. And so this is my projected part. It could be past the line as well. Okay? And then, so here, this part's -4, so I'll go -4 in this direction, up 8 this direction, and then in order, so this is my u1, and then to go back to my original u, I need to go 2 in this direction, up 1 in this direction, so this is my u2. So that's basically how it breaks apart. I'll explain why we use it in a second. Let me do one more with you. You don't have to draw the picture. Let me do one more with you, and then we'll do the other two at the beginning of next time. All right, let's just do one more. Oh, this one actually I made easy on purpose. Okay. All right, so here if we have u and b resolve into u1, u2. In fact, this one you don't have to do it, but let's just do this. So u dot b, we need to know what that is, and we need to know what v, the magnitude of v squared is. Well, the magnitude of v squared here is the square root of 5 squared squared. So it's just 5 squared, which is 25, right? The magnitude here is 5. The other component 0 is just, that's the length, 5. Here, 0 times 5 is 0. 0 plus 2 times 0 is 0, so we have 0. So I have 0 over 25 times v, which is of course going to be 0, 0. So this is, and then here if I have u minus, so this is u1, and then u2. I remember why I did this one. I should have done this one first and then 1 second. I can swap that in my notes. Is u minus u1. So this of course is 0, 2, because 0 minus 0 and 0. So let's look at this real quick. Hold on, let's look at this real quick. So v is 5 in the x direction, 0 in the, so this is my v. My u is 2 in this direction. So if I projected it down, I ended up with the 0 vector. I have nothing, right? And so if the projection is orthogonal, as it is in this case, or so here, my dot product, if they're perpendicular to each other, we have nothing. Yeah, I'm going to go ahead and finish this real quick. So here, these are in the same direction, right? Not necessarily they're opposites, but they have the same magnitude. So here, if I did the dot product here, if I did the dot product u dot b here, and we'll save this one for next time. We'll do another normal example next time. So here, if I have this, so here I have, it's negative 2, 2, so this is my u, and then here, this is my origin, this would be my v. But when we project on the line on which it goes. And so notice you're still on this line. So its projection is going to be itself on this line. And so we'll show that because this becomes minus 2 times 4, which becomes negative 8. So this is negative 8 plus negative 8, which would be negative 16. Here we'll have this equal to the magnitude of v squared. So this becomes, oops. So the magnitude of v squared is equal to the square root squared of 4 squared plus 4 squared. So it's just 4 squared plus 4 squared, which is 16 plus 16, so 32. So I have minus 16 over 32, which is minus a half, right? Oops, I forgot my v. Times v. So my u1 is equal to that, which is equal to minus 16 over 30. So hold on, minus a half v. And minus a half of v would give me negative 2, negative 2. So notice u1 is equal to u2, or is equal to u, so there u2 of u minus u1. Since these are equal to each other, we get the 0 vector. So you can project completely on the line. You can have your projection have nothing, or you can have your projection like this, where it's a mix between the two. We will finish this one. We'll do this one tomorrow after you've sat and slept on it.